Okay, so good day everyone. For this week or for this video, we're going to discuss visualizing search problem, solving problems using tree search algorithms. So here's what you'll find in this lecture. Visualizing search problems, solving using tree search algorithms, specifically breadth first search, BFS, uniform cost search, UCS, and depth first search, DFS. Okay, so how do we visualize search problems? Let us first recall that the problem in AI is composed of the following. So the initial state, configuration of the environment or of the agent, and the environment start of the search. So the successor function given a state S, it provides a list of more probable actions in pair. And the goal state given a state and will give either true or false whether the state is already at the goal state. And finally the path cost given the states or given states will return the cost of the sequence. Okay, so let's try it with a Pac-Man game environment. First, let's identify what the following are and what is the state in this game. Okay, so what are the actions allowed, what are the corresponding costs of these actions, and what does our successor function returns? And lastly, how do we know the goal state given a possible initial state? Okay, given a given back a Pac-Man game environment, the state is basically defined based on the location of the Pac-Man and the food as well as the food status. An action here is either just north, south, east, or west. So basically the keyboard input. And each keyboard input costs one effort for the agent. Next, the successor function. So basically it returns given a state the change in the location of the player or the status of the food. Okay. So how do we represent search problems? So given those components, how do we visualize a search? There are two possible approaches to visualizing a search problem. One is through state space graph. We've seen this last time. The nodes in state space graph is the configuration of our environment. The arrows are leading to the possible successor states. Next is through search trees. The node and arrows are the same as the state space, but the difference is in state space graph, you are shown the big picture of the overall interaction of the states, whereas for search trees, there's just one specific root node at the top and the same specific initial state, and from there you build the state actions. Okay, so here's the generic representation. So for the state space graph, state occurs only one, but in the search tree, same states can occur in three multiple times. So depending on the successor function. Okay, so let's see their comparison clearly. By definition, a state space is a mathematical representation, whereas a search tree is actually just a data structure. In the state space graph, states are showing configuration of the entire environment, including the agent, and for a search tree, what we see is actually a plan from getting one specific initial state to goal state. In the state space graph, you can start at any node, while in search tree, we always start at the root node, specifically at the top of the tree. And in a state space graph, successor nodes are represented using arcs pointing to nodes, whereas in trees, you have arrows pointing to the children nodes. And finally, for the state space graph, you have a set of goal nodes, or you have a specific goal node and you see arcs leading to that goal node. While in search trees, you have an ideal leaf node, and that particular leaf node can be found anywhere or in more than one class. So we can see on the left the state space graph, and on the right the corresponding search tree. So we can see clearly how state interaction are clear in the state space graph, and whereas path is clear given the search tree. Okay, so in creating our agent function for search problems, we will utilize search trees to create the solution, and we will use the state space graph to determine which action is possible and what are the probable resulting states. So tree search algorithms attempts to find the solution by traversing the tree structure from root node and examining child nodes systematically. So search algorithms can be categorized into two. So first is what we call uninformed searches. So these algorithms are often called blind search as its basis of its definition is on its immediate node, depending on the order of exploration or expansion. Here, the algorithm is given no additional information regarding the utility of the node to reaching our goal state. So some of the examples are BFS, DFS, UCS. This tree will be tackling, and I'll leave depth limited and bidirectional for you to explore. So the other one is called informed searches. So unlike an informed search, this family of search algorithms are packed with heuristics to guide exploration and identify which among these states has the higher utility in terms of reaching the goal state. These search algorithms have their own strengths and weaknesses and specific problems. So specific problems has an ideal search algorithm to go by, but to guide us which algorithms to use, the following are some metrics used to determine the algorithm's usefulness. So we have completeness. So this particular algorithm guarantees that it will find a solution. For optimality, this algorithm guarantees that the least cost path will be identified. And we have the time complexity. This is the running time and format, or running time at format, and space complexity, the memory requirement of the algorithm. Okay, so here's the generic search tree pseudocode. So basically we can see that algorithms only vary on which frontier is next to explore. So we have remove choice frontier here, as well as the manner of adding the frontier. And basically we can add a line before the frontier that include choosing which frontier to be added. Okay, so let's start with BFS. So basically BFS, we follow the first in, first out order of expansion, and we prioritize the nearest node. So here's the pseudocode for BFS, and you can see that we just added an explored list. So this is useful so that the algorithm will be able to identify whether the state has clearly or already been explored and therefore no longer included in the frontier list or the list to use to maintain the first in first out queue. Okay, so for the frontier, it will be represented by a black node, and then the explored nodes are blue, and then the unexplored is red regions. Okay, so let's start with our same example. So in our frontier, we have A. So this is a first in, first out queue. Remember. Okay, so from A, once we explored A, it will have a frontier. The immediate next node to be explored is B and F. So we will just add B and F to our frontier. So it's in alphabetical sequence. So that's why I added B first before F. So next to be explored is B. Okay, so you have to base your next move from our frontier. So A is the first one. We added B and F as its immediate states to be explored. Next one is B. So after exploring B, we will add C and F after, or C and E after F. And then next we explore F. So we'll add G. So we'll not add E again because we have already added it on our frontier. Next is C. So we will add D at the end of the list of frontier. The next one is E. So we will add H at the end of our list. So remember, our goal here is to reach J. Okay, so I forgot to mention that. We have to reach from A to J. Okay, so after searching or exploring E, next is G from our list. So we're not gonna add H again. And then next is D. Then we will add I to our frontier. Next is H. So we'll add J and K to our frontier. Next is I. And then the last one is J. Okay. So now we move to a very similar algorithm, UCS, or Uniform Cost Search. So here's the pseudocode for UCS. So we see here that we just changed the priority of exploration. Now we explore based on which node is the cheapest. So we determine which is the cheapest by calling the function path_cost to compare the return values. So the basic idea is it's just a BFS, but now instead of just doing alphabetical comparison, we include the path_cost value and identify which node to explore from the frontier list first. So okay, so for UCS we'll use the same problem, but this time uh, each um, each connecting lines to each node will have a weight, or let's say in real life, let's say this nodes here are the cities, and these lines are connecting them are the roads. So we can imagine that this 7, 4, 5, 3, and the other values are just the time that it takes for you to get to another state, or let's say the distance or kilometers from one city to another. So basically from the first one we have A here. So from A to A we have a cost of 0. Okay, so if we're going to explore from A to B, that would cost us 4. From A to F, that would cost us 5. So we're going to check which of these two has the lowest cost. And with that, B has 4, F is 5, so therefore we go to B. So next one, from B we have 4, and then we take this path here to C, so we'll have 11, and B to E will have 7. Okay, so if that's the case, so from F, so 11, 7, and 5, so which among these three has the lowest path cost? So it's 5. So we're going to explore this F next. Okay, so now updating the path cost. So we have 5 and then 5 here. So G has 10. Now determining which, or choosing or comparing which of these three frontier has the lowest path cost. So we have 11, 7, and 10. So we're going to go to E. So from A, F, and E, we have 5 plus 5. So this E here should be 10. But since in the frontier, the list has recorded 7 and 7 is lower than 10, then still we're not going to replace this into 10. Okay? So from here, we just added another frontier from our list, which is D12. Okay? And also H11. Okay, so from these four values, who has the most, or let's say the lowest amount of path cost? So we have 11, 12, 11, and 10. So since G has the lowest, so we'll just explore this one. Okay, so since it is already explored, so 5, 5, and then 3, so we're not going to update the value of H since its value recorded to the frontier is lower than 13. So H is 11, and then here we gain a 13. So 11 is less than 13, so we're not going to update this. Okay, so from 11, 12, and 11, we have the same path cost, which is C and H. So we're going to follow the alphabetical we were going to explore alphabetically, so that's why we're going to explore C instead of H. Okay, so given this values, so we have 4 plus 7 is 11, 11 plus 6 is 17, so we're not going to update 12 or D as 12 because 17 is greater than 12. Okay, so from here, D has 11 path costs and H has, or D has 12 as path costs and H has 11 as path costs, so we're going to explore H. Okay, so now that H is explored, so 11 plus 10 is 21, 11 plus 4 is 15, and 11 plus 9 is 20. Okay, so based from this 4, which is the next node we have to explore? So 12, 21, 15, and 20. So D has the lowest path cost, so we're going to explore that. So since, as you can see here, I has 21, and then from D, if we add 7, we will get 19. So 19 is lower than 21, so therefore we're going to replace the value of I to 19. Okay, so now we have 3 more frontier in our list. So we'll compare which of these 3 has the lowest path cost. So we have 19, 15, and 20. Okay, so since our goal is to get from A to J, so the next uh, node to explore is J, and that's the time that we have already reached our goal state. Okay, so remember that every time we explore, we check if our current state is the goal state. And for this case, we're not going to explore 19 or letter I and K since we have already reached the goal state, which is J. Okay, so that's it. Okay, so next we will visit another familiar algorithm, which is the depth first search, or DFS. So unlike DFS, the order of exploration for DFS is based on the furthest or farthest node first. So for this algorithm, we will use a frontier stack to enforce a last in first out queue. Okay, so let's have the pseudocode. So looking at the pseudocode on the BFS, the difference from the one using the BFS is just the part for removing the farthest. So for this, we will use the same problem. Okay, so from our frontier, we have A as our starting state. So we'll add that to our frontier. Then once we explored A and check if that is the goal state, so it's not. So we will just add B and F. Okay, so alphabetically, we added B first, and then the last one is F. Okay, so we will explore the farthest. Okay, so farthest first, just like a stack. So therefore, we will explore F the next one, or as the next one. Okay, so F, adding E and G to our frontier list. So we will explore G, and then from G we have added H, so we will explore H, and then from H we have added the frontier I, J, and K. So from our list we have K, so we explored K. Since we already added J in our frontier, so we'll not add it again. And then of course, since we have K, the next thing to explore is J, since K is not the goal state yet. Okay, so here's how we got to from A to J. So those are the uninformed searches, and there's actually more algorithm under this family of search algorithms, but I leave that for you to explore. So here's the table of comparison, so I leave that for you to check, and um, I hope that you learned something new from uh, this lecture. So if you have any question, just send me a direct request. Okay, so thank you and God bless.